welcome to the lecture series on EC368 robotics. The second part in the lecture series on Lagrangian mechanics. Here in this lecture, we will be dealing with two problems. In the previous lecture, we had seen an example problem of a 2 DOF system, how we have calculated the equations of motion using Lagrangian mechanics. Now, in this lecture, we will be dealing with two example problems, two DOF robots we are going to study. So, the first 2 DOF robot that we are studying is of this kind with two revolute joints. We have seen this kind of robot before. This two revolute joint robot, how are we going to use the Lagrangian mechanics for determining the equations of motion? So the first thing that we are going to do is we are going to find the velocity of the center of mass link 2. So this is your link 1 and this is your link 2. Okay. So we are going to find the velocity at the center of mass at this position. This position is called D. And we are going to calculate it by differentiating its position. So first we are going to find out XD. So XD will be this L1, link length L1. This angle is theta 1. Okay. L1, this component in this direction will be L1 projected on this direction. It will be L1 cos theta 1. So L1 C1 plus, since we are talking about D, which is midway through this link 2. So the length will be L2 divided by 2. So 0.5 into L2, and when this is projected, the total angle is theta 1 plus theta 2. So 0.5 L2 into C12. Okay. So there we are going to find the velocity of this. So the velocity component in the x direction is xd dot. Take the derivative of this with respect to time. So minus L1 S1 theta 1 dot, because cos theta 1, this is cos theta 1. So minus L1 sin theta 1 dot minus 0.5 L2 cos theta 1 2. No, to differentiate it, you get it sin theta 1 plus theta 2 into theta 1 dot plus theta 2 dot. Similarly, in this XD we have found out. Similarly, we will find out YD. YD is L1 projected in this direction. So L1 S1 sin theta 1 plus 0.5. Why 0.5 again? Because we are talking about D, which is midway through this link 2. So half of L1. Okay. So now 0.5 L, so half of L2. 0.5 L2 into sine of theta 1 plus theta 2. Remember S12 is sine of theta 1 plus theta 2. So YD dot will be equal to L1 cos theta 1, derivative of this, into theta 1 dot plus 0.5 L2 cos theta 1 plus theta 2, that is C12, into theta 1 dot plus theta 2 dot. So the velocity at the center of mass of link 2, that is at the point D, is Vd squared, is x dot d squared plus y dot d squared. So those two terms that we had differentiated and obtained, just take the first term x dot d squared plus y dot d squared, rearrange them. When you rearrange them, you will get terms like this S1 into S12 plus C1 into C12, which you can rearrange and simplify. So how to simplify, I have given in the notes. Please keep your lecture notes along with you to see your derivations clearly. Now all the steps are listed out. So finally, I will get Vd squared is equal to this. See how we have rearranged this. We have taken all the theta 1 squared, theta 1 dot squared terms, theta 2 dot squared terms, theta 1 dot, theta 2 dot, all those terms we have taken together. In part 1 lecture series, we had seen why we are rearranging like this. So we have collected all the terms and simplified the Vd squared equation. So the total kinetic energy of the system is a sum of the kinetic energies of links 1 and 2. So kinetic energy of link 1 is K1, let us call it. Remember that they are revolute joints. So we have got half into the inertia into the theta 1 dot squared. So half Ia theta 1 dot squared. So this is the kinetic energy expression for a link rotating about an endpoint A. Okay. So kinetic energy of link 2, K2, okay, is half ID. Now we are talking about ID. Why? We are talking about the center of mass of link 2. So that's a point D. Okay. So ID, the net angle is theta 1 dot plus theta 2 dot, that the whole square, plus half mvd squared, your normal kinetic energy equation. Okay. So the total kinetic energy K is this K1 term plus this K2 term, which we have written over here. So that also has now been rearranged like this. And in this, we can see this Vd squared term. All right. So we had already calculated in equation 1 in the previous slide, we had seen the calculation of Vd squared. Now we have to substitute that Vd squared term into this place. Okay. So here we substitute the Vd squared term. We had collected no theta 1 dot squared term, theta 2 dot squared term, and theta 1 dot theta 2 term. So the Vd squared term is substituted in this place over here, and the whole thing is rearranged. How we can simplify this equation, the rearrangement is given very clearly in your notes. Please refer the notes for the calculations and simplification. Now similarly, the potential energy of the system has to be calculated. So the potential energy of the two links, all right, the two links are acted on by gravity. So M1G in first link, L by 2, the center of the first link. So M1G L by 2 into sine theta 1. That is the component in this direction. Gravity acts in this direction, no? So y direction. So that is why sine theta 1. M2G L1 sine theta 1. So whole of link 1 plus the half of link 2. So L2 by 2, the sine theta 1 plus theta 2. So potential energy M1G, this is for link 1. So half of the length of link 1, assuming that L1 is the length of link 1. So this is L1 by 2 into sine of theta 1. Same way M2G, the whole of link 1, L1 sine theta 1 plus half of link 2. So L2 by 2 sine theta 1 plus theta 2. So Lagrangian we know is L equal to K minus P. K we had calculated on the previous slide. So that is the expression. See how we have rearranged it over here. Okay, so similarly, we have to put minus P. So these two terms will come over here. Now we have to find the equations of motion. Now both the joints are revolute joints. So we are going to find the torques. So we have your equation for torque. Ti is dou by dou t of dou L by dou theta a dot minus dou L by dou theta a. This is your general Lagrangian mechanics equation for torque. Now in our specific case, the first joint we'll take, the torque for that will be dou by dou t. Dou L by dou theta I will be dou theta 1 dot minus dou L by dou theta 1. So take your L from the previous slide and dou L by dou theta 1 dot we can do, and we will get these terms over here. Now dou by dou t of dou L by dou theta 1 dot. Dou by dou t of this equation, if you write, you're getting these terms. Look at this. Theta 1 dot will become theta 1 double dot. Okay, so theta 2 dot will become theta 2 double dot, and the various terms inside accordingly. All right. So dou L by dou theta 1 also we have to do. So this is dou L by dou theta 1. So your torque equation as per the equation given on the previous slide is this. Again, see, we have collected all the terms appropriately and placed them. Similar way, we have to find out T2 terms. So dou by dou T of dou L by dou theta 2 dot minus dou L by dou theta 2. So first find dou L by dou theta 2 dot, then dou by dou t of dou L by dou theta 2. So dou by dou t of this we have to find out, and we have got these terms. Okay, and dou L by dou theta 2 we have to find out, and we have got these terms. And so T2 will be, substitute everything, this equation. So this minus this equation. Okay, and we have got T2. We've already arranged all our equations so that we can write it in this format, which we had seen in the lecture series part 1. So T1, T2 is written, collect all the theta 1 dot double dot terms and the theta 2 double dot terms and write it like this over here. Collect the theta 1 dot square term and the theta 2 dot square term. This 0 means in our T1 equation, we did not have an equation for theta 1 dot square. And in your T2 equation, you did not have an element for or a expression for theta 2 dot square. Okay, so then I have theta 1 dot theta 2 dot theta 2 dot theta 1 dot. Both are the same, but for the sake of a symmetry, we are writing it like this. These terms are not there. Okay, only one term was there that had a theta 2 dot theta 1 dot, and these are the remaining terms that don't have these things over here. So we had seen earlier, no, that we have the effective inertia, the coupling inertia, and this was the centripetal forces, this is your Coriolis forces, and this is your gravitational force terms. Now the similar problem for a 2 degree of freedom polar robot. Polar robot, you have one revolute joint over here and one prismatic joint over here. So now your derivation slightly changes. Okay. So R is the length of the robot to the center of the mass of the outer arm. So this link, up to this link center of mass, that is, let us say that the length of the thing is R. So what we can write this as, some variable. So you can see that this thing is going to keep moving. No? So this is going to go in and out. So some variable, let us say x plus half of the length of this outer or the second link, because we are considering only till up to the center of the second link. So some variable over here plus L 2 by 2. Okay. And we can say that because there's just one angle, there's no theta 1 and theta 2, there's just one angle. So let me call that angle very simply as theta itself. So theta 1 that we had earlier, this angle is going to be simply called theta. So now kinetic energy, we have to find the kinetic energy of link 1 and the kinetic energy of link 2 and add them together. So kinetic energy of link 1 is half IA, this is IA. In this particular problem, it has been written as I1, A. It's the same thing. Inertia of link 1 rotated about the point A. Theta 1 dot squared in the previous problem. This we are going to call it as theta dot squared because there's only one angle. We are calling it as theta. Now, doing that, we get this particular expression. Now, like we did earlier, we are going to write it as xd. Okay. XD is the position of D point, that is the center of link 2, is that variable R into cos theta. Okay. YD is the variable length R into sin theta. Why variable length? It was not there in problem 1. One of the joints is prismatic. So now your length is not a constant. It is going to vary. So we had written it as some x plus L2 by 2. So now your xd dot will be, you differentiate this with respect to time and you get this expression. YD dot similarly. So like we did in the previous case, VD squared, that is the velocity at the center of mass of link 2, VD squared is equal to x dot D squared plus y dot D squared. So this term plus this term will cancel out and you will get a very simple term like this. So now you have got the kinetic energy of link 2, you can write it as half I2D. Earlier we had written it as ID. Now this is the same thing. I2 link 2 at the point D. Okay. I2D into theta dot squared plus this kinetic energy term, your normal kinetic energy term, half M2 VD squared. Now your VD squared is there over here. So just substitute over here. So now your K is equal to K1 plus K2. So K1 term is here, K2 term is here. So add these two together. Now potential energy P is equal to M1G L1 by 2 sine theta. We had seen this in the last problem. So M2G, now we don't know, we did our, since it's a prismatic joint, you cannot write over here. We had written over here the term corresponding L1 and L2 in the previous problem. Here we have to write that variable term. M2G R sine theta because the length is variable because the joint is prismatic. So now your L is equal to this K minus this P, which is written over here. So torque we know is dou by dt dou L by dou theta dot minus dou L by dou theta. Okay. So from your L expression from the previous slide, find out dou L by dou theta dot, dou by dou T of that, and dou L by dou theta of the L from the previous slide. So we have got the torque. Torque is corresponding for the first link, the first joint is a revolute joint. So we are corresponding torque we are writing here is written using this expression. This is the term that we get over here. All the elaborate steps and working out is given in the problems. So you can follow from that. So similarly, for the next joint, it is a prismatic joint. So we write force over there. In problem 1, both were revolute joints. So you had torque 1 and torque 2, T1 and T2. In this case, the first joint is a revolute joint. So we wrote the torque. The second joint is a prismatic joint. So we are writing force. So dou by dou T of dou L by dou R dot, your variable length, minus dou L by dou R. So compute dou L by dou R dot here. Okay. And dou by dou T of dou L by dou R dot over here. Okay. Dou L by dou R this. See, this is actually dr by dt. So dou by dou t of r dot will lead to r double dot. Okay, acceleration. So dou L by dou R over here, you take the terms. So F can be computed in this manner. So this is a much simpler equation than the previous case with which had many terms. So first you write the torque of the first joint and then force related to the second joint. Again write it in this format, theta double dot R double dot, theta dot squared R double dot, theta dot squared R dot squared, R dot theta dot R dot, and then the constant terms in order to write it in the format representing the various types of inertia, Coriolis forces, centripetal forces, and the gravitational forces.